let us consider a system, closed system having these two phases and two components. So it is the bicomponent two-phasic system. Bicomponent two-phasic system. The system is closed one and it has two phases. One is liquid phase, which contains these two volatile liquid solution having the mole fraction x1 and x2, and it is since the liquids are volatile, so part of the liquid will be vaporized, and to give the vapor pressure P1 and P2 for the first component and second component, and this will constitute the vapor phase. So each component remains in equilibrium between these two phases. So it is the two-phase equilibrium system, and the temperature has been kept constant, and temperature can be kept constant by keeping this container in a thermostat of a fixed temperature. So temperature is fixed and composition of these two components in the solution are also fixed, and the compositions x1 and x2, that depends on our choice whenever the solutions is being prepared. So whenever x1 and x2 are fixed, temperature is fixed, P1 and P2, these two are also fixed. So this total pressure P, total vapor pressure or total saturated vapor pressure over this solution is equal to P1 plus P2 according to Dalton's law of partial pressures, and this is also remaining constant. So the vapor pressure P1 and P2 could be expressed in a more generalized way, whether that may be generalized way means the solution may be ideal, solution may also be non-ideal. In all the cases, this generalized expression of this vapor pressure P1 and P2 would be applicable. And this type of generalized vapor pressure P1 equal to P1 naught x1 and e to the power alpha x2 square, and P2, the vapor pressure of the second component over the solution, is P2 naught x2 and e to the power alpha x1 square. So this in this general expressions, everything else known except this alpha. Alpha is constant, and very peculiar fact is that the alpha will be the same for both the components, and since P1 depends on x2 and P2 depends on x1, so here both the components are interdependent, means effect of one component or activity of one component or escaping tendency of one component depends on the composition of this other component. So this alpha may be equal to 0 or may not be equal to 0. So when alpha equal to 0, this term will vanish. This term will vanish, this term also will vanish, and in this case the P1 equal to P1 naught x1, P2 equal to x2 P2 naught x2, and this solution is ideal, and this is Raoult's law. Means each component behaves independently, and this is the criteria for this ideal solution. So, but whenever alpha is not equal to 0, and in this case, whenever the solution is ideal, so 2 is equal to 1 equal to 2, 2. And this ideal solution, this solution behaves ideal whenever the total uniformity of the cohesive forces are present in these solutions. This is the intermolecular attractions between the two unlike molecules, and these two are with the like molecules. So whenever alpha is not equal to 1, solution. In this case, the solution is non-ideal. Solution is non-ideal. And so whenever not equal to 0 means the solution is non-ideal, means these three cohesive forces are not uniform. There is no complete uniformity of these three type of intermolecular attractions among the molecules of these two liquids present in this solution. When alpha is greater than 1, alpha is greater than 0 means alpha is positive. It is called the non-ideal solution with positive deviation. And in this case, this one, the cohesive forces between the unlike molecules is less than like molecules. So in this case, the molecules are this solution is less stable, and the escaping tendency of each component from the liquid phase to the vapor phase becomes greater, as the unlike intermolecular attractions between the two unlike molecules is small. So they do not like to remain within this liquid and have a greater tendency to be vaporized. So P1 is greater than P1 not into X1, and P2 also greater than P2 not X2. So these are the ideal P2, these are the ideal P1, and this P1, P2 is greater than the ideal value as predicted by the Raoult's law. So non-ideal solution, this is non-ideal solution with positive deviation, and this solution is not stable. This solution is not very stable. So suppose this is a complete miscible mixture of these two liquids. If we add one component to these solutions, then this solution may lead to from the complete miscible to this partial miscible. Means one liquid may be thrown up, one component may be thrown up from these solutions if there is a large positive deviation. If this one is much less than these two. So this is the case of the non-ideal solutions with positive deviations, and actually in this case heat is being absorbed to break these intermolecular attractions and to form this one. This one is less and this one is greater. So the energy required to break these intermolecular attractions between the alike molecules, so energy will be absorbed. And the third case is that alpha is less than 0, not equal to 0, maybe greater than 0 or maybe less than 0, and that means it is the negative. Alpha is negative. From the expression it is clearly seen that if this alpha is negative, then this one is less than this value. This one is less than this value. So in this case, this P1 is less than P1 naught and X1, and P2 is less than P2 naught and X2. So in this will occur only when this 1 and 2 means intermolecular attractions between the two unlike molecules is much greater than 1 greater than 2. in this case, whenever intermolecular attractions between the two unlike molecules is very high, the solution is stable. Solution is stable. And there will be less tendency for the components to be vaporized. So P1 and P2 are less in comparison to the ideal solutions. And in this case also, since the solution is stable, so if you add some component, either first component or second component to the solutions, this will also become a solutions. Means the solution will be completely, or both the liquids will be completely miscible. Now I like to derive and it is very surprising that if one component, since alpha is same in both the cases, so it is clear that both the components behaves a similar way or in a like way. If one component behaves ideally, then same component also behaves ideally. If one component behaves non-ideal, then other component also behaves non-ideal. Similar, I can compare the two boys are in a room and they are mixed up. But if the one boy behaves ideal, then other also boy's behavior is also ideal. If one boy behaves non-ideal, then other boy also will follow the same pattern. So in this case, now I like to derive thermodynamically what will be the expressions of this vapor pressure P1 and P2 for the in general for ideal solutions and for the non-ideal solutions, and this derivations is coming up from the discussions of our chemical potential of these components in the solutions. As I have told earlier, the components, both the components are in equilibrium with this liquid phase and vapor phase. So the thermodynamics, basic thermodynamics is that we could express in terms of this most important thermodynamical property, the chemical potential. So let us take this ith component. Instead of writing first component, second component, we may write the ith component. And so as the ith component remains in equilibrium in both the phases, the condition is that mu I liquid is equal to mu I vapor at constant T and P. Temperature constant, pressure constant. In this case, both these the ith component remains in equilibrium between the two phases. So this is the condition for the component remaining in equilibrium in different phases. So instead of writing this one, I can write, let us take the solution is behaving solution. We do not put any restrictions for the solutions. It may be ideal, may be non-ideal. But the vapor phase, since the pressure is not very high, so this vapor behaves ideal solid, ideal gas. Pressure vapor behaves ideal gas, but this liquid phase, which is solution may be ideal or may be non-ideal. We shall discuss later on what will happen whenever it is ideal and whenever it is non-ideal. So expanding this one, we know this mu I not liquid plus RT ln AI. AI is the activity coefficient. AI is the activity of the side component. AI is the activity of the side component. AI is similar to xi, and I have also told you that this AI is equal to xi and gamma I. Gamma I is the activity coefficient of the side component, and xi the mole fraction of the side component, and it is the activity of the side component. And whether this solution is ideal or non-ideal, it depends on the value of gamma I. If gamma I is equal to 1, it is ideal. If gamma I is not equal to 1, it is non-ideal. And the departure of the value of gamma I from 1 or unity will measure the extent of non-ideality of these solutions. Let us put here AI instead of xi, and this one equal to mu I naught vapor plus RT ln Pi. Pi is the saturated vapor pressure over the solution for the ith component, and these two are the standard values. These are the standard values for the liquid phase and the vapor phase for this ith component. And if we put AI, if we replace this AI by xi and gamma I, then it will be mu I naught liquid plus RT ln xi and gamma I equal to mu I naught vapor plus RT ln Pi. Here there are two standard terms, and two standard terms could be connected by, if we consider the pure ith component. If we consider this liquid is this liquid phase containing one pure ith component. In the when this ith component in the pure state xi equal to 1, maximum value. And whenever xi equal to 1, it is the pure liquid, no question of non-ideality, so gamma I equal to 1. And for this pure ith component, the vapor pressure over this liquid Pi becomes Pi naught. It is the vapor pressure over the pure ith component. So inserting all these three here, we have mu I naught liquid, and this one 1, this one 1, product of the two 1, ln 1 equal to 0, so this term will not be here, and this is equal to mu I naught vapor plus RT ln Pi naught, and this is the relation. This is the relation between these two standard chemical potentials of the side component in liquid phase and the vapor phase. If we put this one, if we replace this one by this value, then left hand side is mu I naught vapor plus RT ln Pi naught and plus RT ln AI is equal to mu I naught vapor plus RT ln Pi. Again, I like to say Pi is the vapor pressure of the ith component over the solution. So where this xi or AI is the activity of the side component, and this is the pure vapor pressure. It is the vapor pressure of pure side component. Now this one and this one being cancelled. So if we join these two, if we make one term, then RT common, and ln A, ln P I naught and AI, and this will be equal to RT ln PI. So automatically cancelling these like terms, we have this PI equal to PI naught and AI. This is derived thermodynamically without considering this solution is ideal or non-ideal. This is the expressions of the vapor pressure of this I component. So let us expand this expression. This PI equal to PI naught into AI, or we can write this PI equal to PI naught, and instead of AI we can write this XI and gamma I. Now we consider the solutions. What will be the type of solutions depending on the value of this gamma I. Gamma I plays a very important part, and gamma I actually shows us that whether the solution is ideal or non-ideal. So one case when gamma I equal to 1, in this gamma I equal to 1 means in this case activity and mole fractions are the same, solution is ideal. Solution is ideal. Solution is ideal, and so in this case this PI will be equal to PI naught and XI, and this is the Raoult's law. This is the Raoult's law of vapor pressure for this ideal solutions. But in second case, when gamma I not equal to 1, this solution is not ideal, solution is non-ideal. Solution is non-ideal. Whenever some A, whenever this gamma I is greater than 1, gamma I is greater than 1 means the gamma I is greater than 1, activity is greater than Xi, means these solutions, the components, side components is more active than the ideal solutions due to extremely less intermolecular attractions between the first type and the second type of molecules. And in this case, it is non-ideal solution with a positive division. With positive division, and so in this case, this PI is greater than PI naught into Xi. Means the vapor pressure of the I component over the solution is greater than it would be for this ideal solutions. And the B, whenever this gamma I less than 1, then non-ideal solution, it becomes non-ideal solutions with the negative division. it means that whenever this gamma I less than 1 means activity is less than its mole fraction. This condition will arise when this intermolecular attractions between the two unlike molecules, between the two liquids is much more greater than the intermolecular attractions between the like molecules. And in this case, it is non-ideal solutions. Gamma I less than 1 means a solution. Each molecule becomes less active, less tendency to vaporize than the ideal solutions. So gamma I, so in this case, this Pi is less than Pi naught and Xi. So these are all about the expressions of a Pi vapor pressure of the side component over the solutions, and it is deduced thermodynamically considering the most important thermodynamic property, which is the chemical potential. We shall discuss every colligative properties in terms of this chemical potentials. And further, I can show you that this gamma I is very important term, and gamma I of a solution could be determined in various methods. And here this gamma I could be determined by measuring the vapor pressure over the solution of the side component. Means gamma I becomes equal to this Pi divided by Pi naught and Xi. Xi is known while we are preparing the solutions. Pi naught is the vapor pressure of this pure ion component, to be determined by means of manometer, and Pi is also determined by means of manometer over the solutions, and by measuring its right hand side, each term of the right hand side, this gamma I means activity coefficient of the ion component in this solution could be determined by means of vapor pressure method. I can show one very important problem, how the vapor pressures will be used, how the vapor pressure could be used to determine the activity coefficient of any component in a solution. So I have told already that the activity coefficient of any component could be determined by the use of this vapor pressure according to the Raoult's law. And this one problem have been set in GATE 2004, and this problem is the vapor pressure of a pure component P and Q are 700 torr and 500 torr respectively. Two phases are in equilibrium at 1.0 atmosphere. The mole fraction of P in the liquid phase is 0.6 torr and in the vapor phase 0.4. The activity coefficient of this component P in the solution on the basis of this Raoult's law is A option 0.60, B option 0.72, C option 0.92 and D option 1.0. So the problem of this solution could be easily solved by using these formulas. And this given this vapor P naught means vapor pressure of this P component in pure state is 700 torr, and vapor pressure of this Q component in pure state is 500 torr, and the total pressure P equal to 1.0 atmosphere means 760 torr. So this vapor pressure over the vapor pressure of P over the solution is equal to the mole fraction of a P in the vapor phase into the total pressure. This is the Dalton's law of partial pressures, and the vapor phase is assumed to be ideal. Vapor pressure is assumed to be ideal as the vapor pressure is very small to behave ideally. So xp, which is the xp vapor, which is the mole fraction of this P component in vapor phase, is given here. The 0.4. So 0.4, and the total pressure equal to 760 torr, and the product of the two equal to 304 torr. So it is the vapor pressure of this P component over this solution. So this gamma P, activity coefficient of this P component in solution, could be expressed by these relations. Then it is Pp, vapor pressure of this P component, divided by vapor pressure of this P component in pure state, multiplied by the mole fraction of the P component in liquid phase. And this one is 304 torr, and this one is 700 torr, and this one is given 0.6 torr, 0.6 torr. So putting all the values here, the gamma P comes up 0.72. So the activity coefficient of this P component in this solutions is 0.72, and so B. So the correct option for this problem is B. This is an example set how the activity coefficient of a solution could be determined by using this vapor pressure. Of course, there are so many methods to determine the activity coefficient of any component in these solutions. Now, in my next class, I try to describe the Henry's law, which is also very important and have a greater link with the Raoult's law. Thank you all.